All right, welcome back, everyone. Apologize for my absence last Wednesday, but I'm feeling a lot better now. So anyways, hopefully you guys got a chance to watch lesson 21 at some point. But that was probably one of the best lessons to miss because at least or about half of that was essentially a review of polar coordinates from Calculus 2. So the first part of that was just reviewing what polar coordinates are and how those worked in like the XY plane. And then we looked at two different generalizations of polar coordinates, one called cylindrical coordinates, where we just had polar representing X and Y, and then we just kept Z the same. Or we had spherical coordinates, which was represented by one distance and then two different angles, one of which was the familiar theta, the other of which was phi, which was how far you rotate down from the positive Z axis. So what we're going to do with those in the future is we're going to use those to make our integrals easier. And how exactly is that going to happen? Well, let's remember how we made integrals easier before. So let's make another Calc 1 analogy for like the 10th time this semester here. So today we're going to talk about, for lesson 22, change of variables in multiple integration. So let's see how it worked in single integration. With single integration, we have the extremely useful U substitution, where if we see a function g of x frequently occurring in our integral or plugged into something in our integral, and we also see g's derivative in the integral, then what we could do is we could define u to be g of x and then change our integral to just have a bunch of u's. And usually our goal with this is that this formula is complicated, but then this one is easier and it's easier to integrate. So as a basic example of this, let's say we have the integral from 0 to 1 of 1 plus 2x to the 10th. So we could technically do this without u sub. What would be the really masochistic way of doing this without u sub? Anyone know? What would we do? Expand? Yeah, that's right. So we would have to FOIL this out 10 times, and then we could do the power rule. But fortunately, we're not going to do that. What we're going to do is we're going to, we're going to need to give me another pen. Let's see. I literally opened this pen today. Okay, just got it. Yeah, would anyone in the audience be so kind as to loan me a pen here? I think my pen's afraid of changing variables. Thank you very much, sir. I'll give it back at the end of class. All right. Anyways, so what we're going to do is we're going to have u be 1 plus 2x. Now, remember, the derivative of u is also important. So we compute du, which in this case would be 2 dx. Now, we don't have a stray 2 laying around in here, otherwise it'd be very convenient. So what we could do is we could just divide by 1/2, and then we just get the dx, which we certainly have. And with this substitution, we take this 1/2 in du and substitute that in for dx, and then we could just replace this with u. And also remember, another thing that happens when we do u substitution is that our bounds change. Now, a lot of people just don't change the bounds. They may like just keep the same bounds and then resubstitute back in. But if you want to change the bounds, what you do is you take x as 0, put it in here, and that gives you u as 1 for your bottom bounds. And I take 1, put it up here, 1 plus 2 is 3, and that'll be my top bound. And we've changed something that would be really pretty terrible to do directly, but then we make it be something that's actually relatively easy to do. So today we're essentially going to learn how to do this with double integrals. Now there's one difference between this u substitution and what we're going to be doing here. In addition to making the integral easier to do, like the actual integrand part easier to do, we also, and actually this is probably a bigger issue, we want to make the region that we're integrating over a lot nicer. So technically, we're changing the region that we're integrating over when we plug in 0 and 1 into here, but we don't really think about it because they're just numbers. But when we do it with multiple integrals, remember, rather than just having numbers here, we actually have a whole two-dimensional space that we're integrating over. So let me show you what I mean. So let's say we're able to write x, our old variable, as a function of the two new variables, u and v. So since we have two old variables, we now need two new variables. And in the same way, let's say we have y and we were able to write that as a function of u and v. Now, suppose here that we're integrating over some really icky looking space like this. Like this is our domain in x and y that we're doing our integral over. So this is going to be frowny face. We don't want to integrate over this because it's going to be really hard to set up the boundaries for our integral, as we've seen 2 lessons ago here. Okay, but well, then rather than doing this, what we're going to do is instead we're going to do things in terms of u and v. And very often with u and v, if we change the variables to that, it'll be something nice. So maybe like a rectangle, or at worst, like a triangle or circle, something that's really easy to do your bounds over. So the relationship between this and this is g of uv and h of uv. So this one's smiley face, we really like this because it's just a rectangle or an easy shape right here. And this is our goal. We want to find a way of taking our really nasty looking domain and then turning it into something nice. So this is an aspect that didn't really exist with u sub, or even though it did, it was kind of in the background. Didn't really think about it too much. But this is going to be probably in the forefront whenever we're going to be doing any of this substitution. All right, so let's take a look at some examples of this. So let's say we use polar coordinates for this, and this is why we went over polar coordinates before we got to this lesson. So let's say we use the polar coordinate transformation. We have x is equal to r times cosine of theta, and y is equal to r times sine of theta. All right, now suppose we want to take a look at the region where r is between 0 and 2, and then theta is between 0 and pi. Okay, what will that look like for x and y? So if our r ranges from 0 to 2, and our theta goes from 0 to pi, what it's going to end up looking like is a half circle of radius 2. So this is what S is going to look like in terms of x and y. Okay, that's not the worst region in the world. It's definitely not as bad as this squiggly looking thing that I drew up here. But if we drew this in terms of r and theta, though, like if we just looked at our r and theta variables, what will we get then? Well, let's see. R ranges from 0 to 2, and then theta goes from 0 to pi. So what we would get is we would get just a rectangle. And I don't know about you, but I would definitely rather integrate over a rectangle rather than this half circle right here. I mean, it's not too bad to do a half circle, but I would certainly rather do a rectangle. And it's this motivation that rectangles are nicer to integrate over than half circles is going to motivate a lot of our integration choices coming up in the next few lessons. All right, here's a bit of a less familiar example, something that's not in polar coordinates or any of our usual kind of alternative systems here. In this case, we're looking at x is u plus v over 2, and y is u minus v over 2. Now the u's and v's, u goes from 0 to 1, and v goes from 0 to 1. So if we draw our uv right here, this is going to be very simple. It's just going to be a square. It's going to be a square right here in the first quadrant with one edge on the origin right there. Okay, now what's the picture over here? It's a little bit less obvious what the picture is over here. And to help us get what that is, I'm going to make a little chart. So we have uv, and let's see what x and y values those give. So for example, if I plug in u and v being 0, 0, what are we going to get for our x and y? So we have 0 plus 0 over 2 is 0, and 0 minus 0 over 2 is, well, 0. Okay, so this corner of the square goes to the same place. It's still going to be at the origin here. How about we plug in this corner of the square, which is going to be 0, 1. We plug in 0, 1, it looks like we get 1/2, and then negative 1/2. All right, so that's a little bit different. So we go to 1/2, negative 1/2. That's down here. So it turns out that this edge of our square ended up going right here instead. Okay. Now let's check out 1, 0. So if I plug 1, 0 into here, I have 1 over 2, and then I have 1 minus 0 over 2. So that's 1/2, 1/2. That's going to be directly up right here. And then finally, we have 1, 1. So if I plug 1, 1 into here, I have 1 plus 1 is 2, and then that over 2 will be 1. And then I have 1 minus 1 over 2, that's going to be 0. So what is this transformation? This is effectively taking a diamond shape and it's turning it into just a regular old square. Now, this wouldn't be too bad to integrate over, but one annoying thing is that no matter whether we integrated with respect to y first or x, we would have had to split this into 2 integrals because we would have had this upper bound and this lower bound, and then we would have had this upper bound and that lower bound. So it would have been kind of annoying to do this integral this way, or use this region as an integral, but using a square as an integral is absolutely no big deal at all. It's just 0 to 1, 0 to 1. So this is definitely a good transformation here. Why does this make an easier shape when we use different variables? It just depends on the type of function that you have right here. You usually kind of set it up so that the shape that you have here is going to end up being like a rectangle, or at the absolute worst, a triangle. So the 2 shapes are equal in area, or what is the relationship between the 2? They do not have to be equal in area. I mean, it really just depends on what the function is. Kind of like how we could have, back in U sub, we could have picked any, like u equals pretty much any function we would have liked, depending on what integral we could do. We could do the same thing here. We can have any kind of relationship between x, y, and u and v that we want. It's just that some of them are going to be more convenient than others, kind of like how some u substitutions ended up being more useful than others. That's kind of what's going on here. So the sky's the limit in terms of what kind of transformations we can do. All right. So that's all just about drawing the regions. We haven't actually seen an integral yet. So how do we actually do an integral here? How is the integral of f of x y over r related to the integral of f of g u v and h u v? So this is substituting in the substitution over s. So this would be like our r right here, and then this would be our s. So you might think, okay, well, doing the integral over this shape is definitely going to give us a different result than doing it over here. So how do we make sure that those integrals end up being the same value? So that's what we're going to talk about next. And this has a lot to do with like finding your du back in u substitution. So remember, we always had to find the du, and that made the integrals equal to each other. That's essentially what we're going to do now, only this time it's going to be a little bit more complicated. Okay, so suppose we're making the substitution, x is g of uv and y is h of uv. And it sends a region S, which the S is the nice region, in the UV plane into a region R. R is the frowny face region in the XY plane, where G and H have continuous first partial derivatives. If F is continuous, then the double integral over our original region, which is not really that great, we can instead do the integral over the nice region, which is usually a rectangle or something good like that. And then we put in our substitution. But kind of like how we had to have g prime of x back here, we also need to have something involved with the derivatives with this as well. And this is going to be called j of uv, or the absolute value of it. And this guy right here, what is this? This is the determinant of this matrix right here. So we have the x derivative with respect to u, we have the x derivative with respect to v, we have the y derivative with respect to u, and we have the y derivative with respect to v. Now remember, the way determinants work is we do this times this. So I'm going to do partial x partial u times partial y partial v. and then I'm going to subtract, and I'm going to multiply these two together. Okay, now what is this called? Why is it j? This is called the Jacobian of the transformation. And what you could think of this as, like the new du for our integrals. So kind of like how we had to compute what du was every time we did u substitution, we're now going to have to compute what the Jacobian is anytime we want to do a substitution with double integrals right here. All right. So this is effectively just the new du, only it's a little bit more complicated because not only do we have two variables, but each of these variables depends on the two new variables right here. All right. So let's see here. What do we have next? So we can change the variables from xy to uv in a double integral simply by replacing dA with the Jacobian times du dv. And this is what I was talking about. This is effectively your differentials happening here. So this is going to be the determinant of this matrix. So we have that determinant times du dv. So this is effectively our new du right here. Okay, this is kind of scary looking. There's a lot of stuff going on here. Let's go ahead and take a look at an example here. And let's take a look at a familiar example. So let's say we want to use a coordinate transformation for polar coordinates. So we actually saw this a little bit earlier in class. So sometimes it's nice to use x as our cosine of theta and y as our sine of theta, because that's particularly good at representing circular regions because it's polar coordinates. So let's say we wanted to turn our integrals in terms of x and y into integrals with r's and thetas instead. So we want to go from x and y to r and theta. What would the Jacobian be? What would the thing we would need to stick in our integral in order to do this be? Well, let's see. J of r and theta, that's going to be partial x, partial r, partial x, partial theta, and then we have partial y, partial r, partial y, partial theta. Okay, so let's see what this is right here. Partial x, partial r. Let's see, the derivative of this with respect to r is cosine of theta. Now the derivative of this with respect to theta is going to be negative r sine of theta. Now let's go to y. So we do partial y, partial r. We get sine of theta. And we do partial y, partial theta, and we get r cosine of theta right here. Okay. So now we're going to take the determinant of this matrix. We have cosine of theta times r cosine of theta. That's r cosine squared of theta. I bet you guys can see where this is going. And then we have this times this with a negative. So the negative and the negative there will cancel. And then we have r sine squared of theta right here. Okay, well, that's kind of nice because we can factor this and we have our old friend cosine squared plus sine squared, aka 1. So it turns out that our Jacobian is just going to be r for this right here. Okay, now what does this mean? All right, so we computed this, we get r. What is that saying? It's saying that we have if we have an integral of f of xy dx dy or something like that, then that's going to be the same as the integral where we substitute in the new variables. So every time I see an x, I'm going to replace it with an r cosine. Every time I see a y, I'm going to replace it with an r sine. Now remember what this is. So this turns into the new differential, which is the Jacobian r, and then times the new variables. So we stick the Jacobian right here, and then we have the new variables. So if we want to switch over our rectangular integral into a polar coordinate integral, all we need to do is change over our formula into polar coordinates, because that's the main thing we want to do. But then after that, we're just going to stick r right here. And this is the Jacobian. And you can imagine this again as like your du. Kind of like how you can't just plug in things for a u sub and not have the du there as well. It's kind of like that here. You can't have this without the Jacobian here. Is it possible to have a matrix of 3 columns? Yes, it is, but we're not going to talk about that now. Yeah, two is enough for now. Okay, so let's go ahead and actually use this and compute an integral. So let's say I want to compute the integral of e to the x squared plus y squared dA, where r is the region that lies within the unit circle, x squared plus y squared is 1. So anytime we have any kind of circular region that we're integrating over here, it's usually a good bet that we're going to translate this into coordinates. What is the info behind the Jacobian? Is it just one of those things we need to accept? It's mostly that way. Like the best I can explain it is it's just kind of like du, kind of like we needed to compute du is f prime of x dx when we do a u substitution. The Jacobian is essentially the higher dimensional version of that. I can't get into more details about the Jacobian unless we talk about matrix multiplication, and we're going to save that for another class. All right. So anyways, let's try to convert this into polar coordinates. So there are 2 reasons why we would want to do this. The first reason is that I can't do this integral right here. As written, I can't do the integral of e to the x squared plus y squared dx dy or dy dx. I just can't do it. It's too hard. So I want to make the integral easier to do. And then also another reason, so I'm going to write these down. So substituting makes the integral easier, or in this case, it makes it possible. The second reason why we would want to substitute is that the region is expressed better in polar coordinates. So while this isn't as bad as that really kind of weird squiggly picture I drew earlier, our domain isn't that bad. It is easier to write this down in terms of polar coordinates because that's just r equals 1 for that right here. Is it like where we needed a number or function with the dx to equal du for most times we use u sub? It's exactly that. Yeah, that's what I was saying here. Yeah, so it kind of takes the role of du is f prime of x dx. That's effectively what's going on here. You need to look at the derivative of your transformation. That's more or less what's happening here. And the Jacobian has all possible derivatives. It has your derivative of x with respect to these 2 variables and your derivative of y with respect to these 2 variables. So it has every possible derivative there. All right, but beyond that, unfortunately, we're going to need to take that as just something we need to do for this. All right, anyways, let's go ahead and transform this into a new integral. So let's go ahead and see how this actually works. Okay, so presumably this is going to be, I don't know, dy dx or something like that. Now, if we want to change our y and x's into polar coordinates, remember the way that we do that up here is we take these and then we replace it with dr and d theta like you'd expect, but then we also have to put the Jacobian in there. So we're going to end up with an extra r when we do this. So we have r dr d theta. And then we could change the rest of the function into polar coordinates. So what am I going to change this into? What's the new way that I'm going to write e to the x squared plus y squared? That's right. It's going to be e to the r squared. And now you see why this is a good substitution. Now this is turned into a much doable integral because we could just do u is r squared and then du will be r right here. Yeah, where did the r come from? Remember, this is the same thing as this because you need to put in the Jacobian whenever you do any kind of substitution, and the Jacobian for polar coordinates is r. Why is r squared? Because x squared plus y squared is r squared with polar coordinates. All right, now what is our integral going to be over? Well, let's see with R, where we're trying to represent the circle, right? The unit circle. So the unit circle has R values ranging from 0 all the way out to 1. And then the unit circle has theta values ranging from 0 to 2 pi. So rather than some icky kind of like putting half circles on the top and bottom here and then -1 to 1 there or something like that, we're instead just replacing everything with constants right here. How do we know what the Jacobian is if we've never solved the determinant of the matrix? Well, if you use some kind of new system other than, say, something familiar like polar coordinates, you need to take the determinant of the matrix to do that. Kind of like how we had to compute whatever this was from scratch every time we did a U substitution. Will the bounds always be those for polar coordinates? No, they won't. Although they'll always be that with polar coordinates in the unit circle, though. But we may have other shapes that aren't the unit circle. How do I find the integral bounds? The lowest R value we have is 0 for the unit circle, and then the highest R value we have is 1. And then we go, for what theta values do we have? Well, we start at 0, and then we go all the way around the circle to get 2 pi right here. Yeah, what's up? Oh, well, effectively, this was the work for this right here, because it's the same substitution. We're using polar coordinates here, and we're using polar coordinates right there. Yeah, so the question was, why didn't we need to do this stuff for this step right here? And it's because it's this, you can effectively imagine this as like a two-part problem. This was the transformation we're using earlier. All right, and let's do this real quick. So now we're going to use regular U substitution on the R integral. So du is R squared, so du is 2R dr. And technically, you can imagine U sub as a Jacobian as well, but it's the determinant of a 1-by-1 matrix, which is not very interesting. So I'm going to divide by 2. And then we get R dr, which shows up in here. All right, so this integral, we have 0 to 2 pi. And then we have R is 0 to R is 1. 1/2 e to the u du d theta. All right, so we did U sub to make this part doable right here. So now let's go ahead and just do this integral, but it's the integral of an exponential function. So it's going to be the same thing. So we have 1/2 e to the u, but then u was R squared. All right, let's see. I'm going to go ahead and plug in 1 and 0 into this. So we have 1/2, and then we have e to the 1 minus e to the 0, which is 1 here. All right, so that's what we get out of this. And then now we're just integrating a constant with respect to theta. So this is going to be, I'm running out of space here. It's going to be 1/2 e minus 1 theta from 0 to 2 pi, but that effectively means I'm just going to put 2 pi in for my theta here. So the 2 pi partially cancels with the 1/2, and we get pi times e minus 1, just as we run out of room at the corner of the page here. But the main part of this problem, so this was nice practice doing an iterated integral, but the main part of this problem was understanding how these two parts are equal right here. What's the upper bound of the second one? It's 2 pi. Yeah, so this is the integral from 0 to 2 pi, so we can go all the way around the circle. Oh, before that, what's the upper bound of the second integral with respect to du d theta? Oh, it's r equals 0 to r equals 1 right here. Is there a way to tell if a problem is just too hard and we should switch to polar? If you see things that look like this, x squared plus y squared, that's a good sign to switch to polar. But mostly it's if your domain is circular in some way, I would switch to polar in that case. Okay, let's do something that isn't polar. All right. So let R be the region bounded by the lines x minus 2y is 0, x minus 2y is -4, x plus y is 1, and x plus y is 4. And they were kind enough to draw these lines for us right here. Now what we need to do is we need to evaluate the integral 3 times x plus y. Okay, now we could do this as is, but that would not be very fun because you'd probably have to divide up your region like this and then do 2 different double integrals. So that's not that great. So what we're going to do is we're going to try to use our substitution to help make things better. And this time we're only using substitution for the second reason. Doing the integral of 3 times x plus y is not challenging. We can definitely do that integral. So this time we're purely using it for the new reason in that this region is not really that great. Now, how do this time they didn't tell us to use polar, or they didn't give us any kind of u and v. So what are we supposed to do here? Well, we're going to use kind of the same reasoning that we used back when we learned u substitution. If we see something appearing a lot, that's probably a good thing to make be your new variable. So we have these two guys, they show up twice. Why don't I make that be u? And then we have this showing up both here and here and in the integral. Well, let's make that v. Let's just see if this works out. Okay, so this means that we're making u be x minus 2y and v be x plus y. And you could have done this the other way. You could have called the other, like you could have called this v and that u. It doesn't really make a difference here which one you call what. All right, now we need to figure out, so if we're going to convert this integral to u's and v's right here, we need to figure out what the Jacobian is. So we need to know what j of uv is. And remember, that's partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. The only problem is that we don't have these integrals with respect to, we don't have this as x equals something and y equals something. We have a u and v equals something. So what I'm going to do is I'm going to solve these for x and y. I want x to equal something with u's and y to equal something with, or sorry, x to equal something with u's and v's, and y is to be something with u's and v's. So what I'm going to do is I'm going to subtract these equations to cancel out these x's. So I have x minus 2y minus x plus 2y. So the x's will cancel out. And I'm going to have negative 2y minus y. So I have negative 3y. And I'm going to divide by negative 3. And I get v minus u over 3 is y. Okay, so now it should be easier to get these derivatives here. So let's go ahead and plug this in here and get what x is. So v is going to be x plus v over 3 minus u over 3. And if I subtract these over here, I get 2v over 3 plus u over 3 is x. All right, so now I have my equations the right way up, and now I can go ahead and take the Jacobian. Although I'm going to teach you guys a shortcut of doing this after this problem, but this is kind of the traditional way of doing it. All right, so we have partial x, partial u. Let's see, the u derivative of this will be 1/3 right here. Wait, what? What's going on here? I'm pretty sure I did this correctly. So we subtract 1/3 v over here, and we get 2/3 v. And then I add u over 3 over here to get u over 3. No, don't worry. I get turned around with these fractions all the time too. It's really easy to add something when you need to subtract. All right, so let's do partial x, partial v. That's 2/3. Partial y, partial u is negative 1/3. And partial y, partial v is 1/3. All right, so what do we get from this? We have 1/3 times 1/3 is 1/9. And then we subtract and do 2/3 times negative 1/3. So that's going to be plus 2/9. So that gives us 3/9, or 1/3 right here. All right, so 1/3 is going to be our Jacobian. So we're going to need to stick this in with our integral once we convert it over. Now, one thing about converting our integral is that the bounds are going to change, right? Kind of like how you would use substitution, the bounds change then, they're definitely going to change for this right here. So what are our bounds for u and v now? Well, they actually kind of say them in the problem, right? So we want it between the lines x minus 2y is 0, x minus 2y is -4. That's the same thing as saying we want it between u is 0 and u is -4. So u equals 0 is the line right here, and then u equals -4 is out here. Okay, that's nice. It looks like we're shaping up to get a rectangle here. And then the other two, we have x plus y is 1, x plus y is 4. Well, that's just the same thing as saying that v is 1 and v is 4. So we have v is 1 right here, and v is 4 right here. And thankfully, we end up getting ourselves a nice rectangle right here. So now our bounds are going to be much easier to set up because the easiest double integrals are ones where we're integrating over a rectangle. That's what we learned on the first day of doing double integrals. Okay, so Dr. Huang was kind enough to provide us a whole page with which to do this integral. So let's go ahead and use it. U is -4. Yeah, that's what it said right here. Okay, so our original integral will now be the integral of 3, and then we need to change this into u's and v's, right? So this was literally what v is, because remember, u is x minus 2y, and v is x plus y. So this is just going to turn into 3v, and then we have the Jacobian times du dv. And let's see here, du, so the lowest u bound is -4, and the highest one is 0. And then v goes from 1 to 4, like that, right here. All right. So one thing I don't know if I mentioned this earlier, but I should definitely say it now. If you ever get a negative Jacobian, just get rid of the negative sign. The Jacobian should always be positive here. So if we ended up putting this in the other order, for example, and we got -1/3, we just get rid of that and use 1/3. All right. So now we plug in our Jacobian, which we found to be 1/3 right here. Why is it absolute value? That's diving a little bit deep into what I was talking about earlier, but loosely speaking, it's a scaling between the different areas of these right here. So this rectangle is going to end up being 3 times the size of this one here. So in order to counteract that, we put in the 1/3 right here. That's why it's absolute value. So since it's just a scaling, we're going to keep it positive. But thankfully, these cancel out. All right. Now, I want to remind you guys of a technique for doing double integrals that I think I kind of just mentioned it in passing, or maybe we did one example, but then we kind of ignored it. If we have only one variable showing up for a double integral, then what we could do is we could split our integral up like this. So we can have the integral from 1 to 4 of v dv times the integral from -4 to 0 of du. So remember, if you have just one variable, or maybe you just have 2 variables that are just multiplied together, remember you could split up your integral to be just the product of the 2 right here. This is a very handy trick. So the integral of v dv will be v squared over 2 from 1 to 4. And then meanwhile, with this integral, the integral of 1 du will just be u. That goes from -4 to 0 right here. All right. So I'm going to plug in 4 right here. So I have 16 over 2. And then I subtract 1 over 2. Meanwhile, with here, I have 0 minus -4. So I have 15 halves times 4. What is that? That's going to be 30. So we end up with a value of 30 for this integral. Actually, we did not need this whole page at all. Like, look, we still have a bunch of blank space. So that was just a little psych out. We didn't actually need that much space for this integral. And the reason why we didn't need that much space is because we did the substitution. If we would have neglected to do the substitution, then we probably would have filled up this entire page doing 2 separate double integrals with these bounds right here. So that would not be as great. That would take the whole page. Draw a raccoon. Yeah, unfortunately, I don't think we have time in class for that. All right. Oh yeah, let me talk about this. So earlier we had to kind of flip our equations around in order to get x and y in terms of u and v. But in practice, we don't actually have to do that, because if you want the Jacobian, we could do the determinant of this matrix. This is like the normal way of doing it, the Jacobian. Or if we have u and v in terms of x and y, we can do the Jacobian that way and then just do 1 over our answer. So let me show you what I mean. So another way of doing the determinant from the same problem would be to do partial u, partial x, partial u, partial y. So we kind of flip these upside down. And then we have partial, v, partial x, partial v, partial y. And then we're just going to take the reciprocal of whatever we get for this. All right. So let's see here. Partial u, partial x is 1. Partial u, partial y is -2. Partial v, partial x is 1. And partial v, partial y is also 1. All right, so, oh yeah, and this is reciprocal. So we have 1 times 1 is 1. And then we subtract -2. So we have the reciprocal of 3, which ends up being 1/3 right here. So why did we do it that way if we could have done it this way? To illustrate why this way is better. So you don't have to end up solving this like that in the future. Just go ahead and do the derivatives of whatever you got. And if you started with u and v equaling something, then you're going to need to take the reciprocal of that. So just remember the reciprocal part. We could have had a raccoon? No. I'm sorry. Yeah, there definitely wasn't been time for that. All right, we got one more here. Let's see here. Let R be the region bounded between the lines x plus y is 1 and x plus y is 3. And the curves x squared minus y squared is -1 and x squared minus y squared is 1. Use the change of variables s is x plus y and t is x squared minus y squared to evaluate this integral right here. All right, although I guess this should be s and t. Okay, so this time they were kind enough to give us what our new variables should be, although even if they didn't, it would make sense to pick our new variables being x plus y here for s, and then this for t, or the other way around, because these show up a lot in our problem. All right, so let's see here. What kind of region we'll be integrating over? Well, let's see. So it looks like s goes from 1 to 3. We have 1 here and 3 here. So 1 to 3. And then t goes from -1 to 1 based on this right here. So it looks like now we're going to be integrating over this rectangle right here. This only works well with symmetric bounds originally, right? I'm guessing you mean like something is a number, something is another number. No, you could do it in more instances than that, actually. If you look at some of the now you try it's, there's one that isn't like that. So you could use this in more situations. All right. So let's see here. So this is the region we're integrating over. Now remember, we always need to compute our Jacobian. Now let's use the new way of doing the Jacobian. Oops, we're not using use. We're doing J of S and T. So that's going to be the reciprocal of partial S, partial X, partial S, partial Y, partial T, partial X, and partial T, partial Y. So we're just using the new technique that we just learned right here. All right. So we have partial S, partial X. What is that? Well, remember, S is just X plus Y. So that's going to be 1. And then partial S, partial Y, that will also be 1. Now remember, T is X squared minus Y squared. So partial T, partial X is 2X, and partial T, partial Y is negative 2Y. All right. So let's see here. We do 1 times negative 2y, we get negative 2y, and then we subtract and do 1 times this. All right, so then we end up with negative 1 over 2x plus 2y. Now remember, we're going to be putting this Jacobian in our new integral. So this is one downside doing it this way. You're going to get x's and y's in here. But there is an easy way to change this to be an s's and t's. We could factor out a 2, and we see an x plus y. And that's good because we see an s right here. So we have negative 1 over 2s. Is there a reason why we were doing partial derivatives of s and t in terms of x and y and not the other way around? Yeah, it's because we already know the equation for s and t in terms of x and y. If we didn't want to do it this way, we would have had to solve for x is something and then y is something, and that would have been terrible in this case because we would have had a quadratic. All right. All right, so we have negative 1 over 2s, but then remember, we want the absolute value of the Jacobian, just like chat was saying. So we're going to have 1 over 2s right here. All right, now we're ready to switch into our new integral because we have the Jacobian. We know what region we're doing this over. Okay, so let's see here. So we have our double integral. Oh, let's take a look at this though. So, well, e to the x squared minus y squared, we know what that's going to be. That's going to be e to the t. Okay, so that part's not a problem. How do we get x minus y? Yeah, oh, you guys were on the ball here. That's right. So how are we going to get x minus y? We remember that x squared minus y squared over x plus y is x minus y. And what's another way of saying this right here? This is going to equal t divided by s. So another way of saying x minus y here is t divided by s. So this is what the integrand turned into. Now remember, we need our absolute value of our Jacobian, so we're going to stick that in here. So this was from the original function. This is from the absolute value of the Jacobian, and then we do ds dt. All right, let's see. Our s goes from, what did it go from? 1 to 3. And then our t goes from negative 1 to 1. All right, so now this is our new integral that we're going to use here. All right, so let's see here. Now, once again, this is, if we rearrange this, let's rearrange it a bit. This is t e to the t times 1 over 2s squared, if we rearrange it. So this is a function of t times a function of s. So once again, we could use that double integral trick right here to integrate each of these separately right here. To re-explain how we got the t over s, t is x squared minus y squared, s is x plus y. And if you use the difference of squares and bring this up, x squared minus y squared is x minus y times x plus y. Don't feel bad if you didn't see that right away. When I was going through the lecture notes earlier and doing these like on my own, it took me a second to realize, oh wait, that's what they want you to do. So don't feel bad if you didn't like instantly see that right away. It's okay. All right. So now, since we can split these up, we're going to split this into the product of two different integrals. So we're going to have the integral from 1 to 3 of 1 over 2s squared ds. And then we're going to have the integral from -1 to 1 of t e to the t dt right here. And remember, we can do that whenever we have a function of t times a function of x. Or in general, a function of one variable times a function of the other. We could split the integrals up like that. All right. Ooh, looks like we're running out of time here. They gave us a whole page for this one too, although we're almost done with it. So I don't know why we need that much space. I'm going to do this integral. I do the power rule, raise this to be a negative first power, and then divide by -1. Okay. Long story short, if I use IVP on this, I'm going to make it the short story. It's going to be t e to the t minus e to the t. If we do integration by parts with u is t and dv is e to the t. All right, so then I go ahead and plug this in, and I have -1/6 plus 1/2. And then if I do it over here, if I plug this in, I have 1 e to the 1 minus e to the 1 is 0. All right, and then I plug the negative in here, and I'm going to have what? It looks like I'm going to get 2 over e for that. So 1/2 minus 1/6 is 1/3. So we end up with 2 over 3 e, like that. All right, so there we go. So we managed to speed through the last part of that. The main part of this, though, rather than doing these double integrals right here, the main part is realizing how to set this up. That's going to be the theme of this whole chapter. The hardest part is setting up the integral. Once you set up the integral, then it's usually just kind of a grind to get down to the specific number. But if you set up the integral right, then you've done most of the hard work there. All right, we are out of time now, so I will see you guys next time.